College in London, and the title is Particle Approximations for Strong Solutions of Linear SPDEs with Multiplicative Noise. Please welcome.
Thank you very much. Okay, so let me start by thanking the organizers for the invitation to give a talk at this final meeting of the SPDE program. As you can see from the title, I would like to present two particle methods for the numerical approximations of the Zakai equation. Zakai equation is a linear SPDE with multiplicative noise and plays a central role in stochastic filtering, and that's where the motivation of this work comes from. The first of the two methods is a Monte Carlo based method. In the context of filtering, is known as a particle filter or as a sequential Monte Carlo method. The second one is not a Monte Carlo based method. It uses some of the recent developments in the theory of approximations for stochastic ordinary differential equations. In particular, it uses the results obtained, the methods obtained by Kusuoka, Lyons, and Victoire. What I intend to do is to present the Zakai equation and motivate it through the description of the filtering problem. I will then spend some time explaining how one should rigorously define, one should rigorously introduce an approximation of an SPDE, or in general an approximation of a measure process. I will then present the two methods and conclude with some final remarks. The second part, the second method, is based on a couple of papers. One of them will appear in the Oxford Handbook of Nonlinear Filtering, and you still have some flyers over here if you are interested to get one of these handbooks at a discounted price. The second one appeared a few years back and is based on work with my student Sadia Ghazali. The first method, if you want to learn more about the first method, which is, as I said, in the context of filtering, is called a particle filter or a sequential Monte Carlo method, then I would like to recommend my book, which has appeared last year and Springer Verlag. So I've done my bit in advertising the various publishing companies, so now let's try and advertise my own work. Okay, so we start with a probability space on which we have defined an m-dimensional Brownian motion, and the solution of the Zakai equation, we think of it as a measure-valued process. There was a stick somewhere here. Is there? All right. So, as opposed to probably most of the talks that we'll present it throughout this workshop, in this area, it's better or more natural to work with weak solutions, in the sense that the Zakai equation, you look at the Zakai equation in terms of integrals with respect of test function with respect to the solution. So rho T of phi here is going to be the integral of some suitably chosen test function with respect to our random measure, and the equation satisfied by rho T of phi is given by this expression. So we have an initial condition, and then we have a sum of two terms, one which is deterministic and one which is driven by our finite dimensional Brownian motion W. For the deterministic term, we have in here rho s of a phi, where a phi is a second order differential operator. It's basically the infinitesimal generator of a diffusion process that I'll present on the next page. And in the stochastic term in here, we simply have rho s of gamma k times phi, where gamma k is just some function which we assume that both gamma k and all the other coefficients satisfies sufficient conditions so that we have a solution of this equation, and the solution is unique. So I'm not going to go into the conditions under which this equation has a unique solution. They are quite well known. The equation has been studied for many years now. I just want to say that I'm choosing this simpler form of the Zakai equation. What follows can be applied to much more general forms. For example, you can have a zero-order term here added to the deterministic part. You can have a first-order term added to the stochastic part. You can even have an infinite-dimensional Brownian motion. It's not my intention to present these results in the more general case. I just wanted to convey the nature of the results and the open problems that surrounds these results. I emphasize the fact that, as in the previous talk, I'm interested in the strong solutions. That means that what is given to me, I have the initial condition of the Zakai equation and the driving Brownian motion, and out of it I want to extract, I want to approximate, I want to simulate rho t. So I want to get an approximation of rho t where my data is this quantity. Okay, so why the Zakai equation? Well, the reason is that it plays the central role in filtering theory. So let me just describe briefly what the filtering problem is. We start with a probability space omega f p tilde. Now this p tilde is not the same as the p on the previous page. The two are absolutely continuous with respect to each other. You can toggle, and you will be able to toggle between the two of them via a Girsanov transformation. And on this probability space, we have two Brownian motions, v and u, and we have a process x, which is called the signal, which is simply a diffusion process whose infinitesimal generator is the second order operator that you've seen on the previous page. And we have another process, w, which in the previous page was just the driving Brownian motion. Here is given by as a Brownian motion plus drift, and obviously you can eliminate the drift by doing the Girsanov transform, as I will show you on the next page. And the idea is that you want to estimate x, the signal x at time t, given the information that you obtain by observing w from time 0 up to time t. In other words, so this is the conditional distribution of xt given this observation sigma field, and we denote this by nu of t, and obviously nu t of phi. If you take a test function phi and integrate with respect to this conditional distribution, all you obtain the conditional expectation of phi of xt given the sigma field generated by the observation process. And the theorem here and the connection with the Zakai equation is that if you take the solution of the Zakai equation and normalize it, that means that you take the total mass, you take the mass of rho t, this is a measure, it's a random measure, and you divide rho t by the total mass, you obtain a random probability measure, and this is exactly all conditional distribution. So you have this duality. You know, if you want to approximate nu t, you can approximate rho t, normalize it, and you find nu t. Vice versa, if you want to approximate rho t and know how to approximate nu t, then obviously you have to approximate nu t, find a way to approximate the total mass, and then get an approximation for rho t. And it turns out, so you know what I'm going to do from now on, I'll go on with this duality. As I go on, I'll always tell you how you do them, the two of them in parallel. But it turns out that it's better, it's more stable to get directly the normalized version of rho t, multiplied by the approximation of the total mass, and then get the solution of the Zakai equation. Okay, so oops. So as I just said, under P tilde, the process is not a the process W is not a Brownian motion, but it can become a Brownian motion by introducing a relevant exponential martingale and making sure that P, the radon-encoding derivative of P with respect to P tilde, is given by this exponential martingale. So that's how we go from P to P tilde, and of course you can come back from P tilde to P. Sorry, that's how you go from P tilde to P, and then you can come back from P to P tilde by taking 1 over this process. Now, it's fairly easy to show that the solution of the Zakai equation satisfies this stochastic representation. So what you have rho T of phi. So you take a test function and integrate it with respect to the solution of the Zakai equation, and this is going to be equal to this quantity. So what you have in here, you take the test function, you estimate it at the current position of the signal, and then you multiply this expression, the phi of xt, by this exponential martingale in here, which is just 1 over that. Okay, so it turns out, so under P, x and w are independent with respect to each other, and when I condition in here, one way to think about these things is that somehow the path w is fixed, and you just take the expected value of this quantity with respect to the law of x. Now, putting this in a different way, the rho t is absolutely continuous with respect to the law of x, and the radon-encoding derivative is given by this quantity. So what you could do, you could generate independent realization of this process x, and for each independent realization you could compute or approximate these exponentials, and via a strong law of large numbers you can get an approximation of rho t of phi. And indeed, the first of the two methods exploits this simple idea. The only addition is that you would want to find a way to minimize the variance of this quantity. The variance of this quantity increases exponentially, and you will see how this is done. Right, but before I go into that, I'd like to say a few things about how you rigorously introduce numerical approximations. And the reason for wanting to do that is that when you look at papers in this area, a lot of the papers in this area present ad hoc methods. There isn't that much rigor in this area, especially from the papers written by practitioners. So I have enumerated there 3 different parts that a complete description should contain, and I have a pictorial description of this fact. So the first to start off, what you need to do, you need to identify the class of approximations that you are going to work with. Right? So that should be the first of your description of the approximation. And for example, in the case of particle filters, we work with approximations of this form, with approximations that are empirical distributions of clouds of particles that have random positions v and g of t, which will evolve through the space of the signal, and each of these particles will carry a weight. And if you write down the empirical distribution of this cloud of particles, you get this expression, and we will always be looking for approximations of this form for the solution of the SPDE. So I call this class of possible approximations Bn, and the way to think about this is that you have slices of the set as n varies, and ideally as n varies you should get closer and closer to the target distribution, to the solution of the SPDE. So that's the first one. The second one, you have to specify exactly how the approximation evolves. So this is mostly done by describing the algorithm. And the third one, and sometimes this is kind of lost in the mist of details presented, is you have to say clearly from the very beginning how are you going to measure the error. How are you going to measure the error? In other words, how are you going to estimate the distance between the approximation and the solution of the SPDE, your target distribution. Okay. So before I go on, let me just say something about the two sets A and B. It turns out that the two sets A, the set where rho t, the solution of the SPDE, evolves, and the set of approximations are disjoint. That's on one side very good news. Why is it a good news? Well, it's good news because this rho t is usually evolves on an infinite dimensional manifold, right? So you can choose there's not a unique way to choose way A, but even if you say, okay, I'm going to choose the minimal manifold that contains the evolution of rho t for any choice of y, there are results that say that you cannot, this minimal manifold is infinite dimensional. That's one thing, and the other thing is that rho t is usually absolutely continuous with respect to Lebesgue measure, and that's not such a good thing if you want to compute rho t of phi in, say, dimension 6, 7, 8, because you'll have to integrate over a very high dimensional space, or a high dimensional space. By contrast, Bn is finite dimensional. Why is it finite dimensional? Well, it's finite dimensional because what we have here is dictated by what? The dimension of Bn is simply n, the number of particles, times the dimension of the state space for each of these particles, which is going to be exactly d, if d is the state space where this signal evolves. So it is a high dimensional manifold, but it's a finite dimensional one, and that's good news because we can very easily generate or sample from distributions from solutions of SPDEs. These are Bn will solve a stochastic differential equation. So this guy is finite dimensional. It's easy to approximate, or it's easy to generate the particles Vn, and the weights will be functions of these particles. The dimension of this is high, n times d, but that's not a huge problem. Current state of the art is that one can work with, say, 100,000 particles in 10 dimensions. So, working with on a manifold of dimension 1 million, it's not a problem. Going beyond that, it begins to be a problem. And if I have time, I'll say why it's a problem if you go beyond, say, 10 dimensions. Okay, so another advantage of this choice of approximation is that if I want to compute rho t and a phi, for example, I like to choose phi equal to the identity and just compute an approximation of the mean of rho t, all I need to do, I just have to have a sum in here. So no more an integral over a high dimensional space, but just a sum. So this is very easy to do no matter how high the dimension of the space is, and that's what makes particle approximations very preferable when you go beyond dimension 3 or 4 for the state space. Now, these are the advantages. What are the disadvantages? Well, the main disadvantage is that it is hard to estimate the distance between the approximation and the solution. If you try to look at, so this is, imagine that this is the space of all finite measures. If you look at the total variation between the two measures, then this is infinite. One of them is usually smooth, usually absolutely continuous with respect to the Lebesgue measure. The other one is just a random measure, so the total variation is infinite, no matter how large n is. And similarly, if you choose any other norm that is absolutely continuous with respect to the total variation norm, for example, the Hilbert norm, you'll have the same problem. And then the question arises, well, then in what sense do you actually get an approximation? Is, ideally what you should have this distance between the two of them, the error going to 0 as n increases. And the possible choice, and you'll see results that contain this choice, is as follows. So what you do, you take an arbitrary phi, which belongs to a large class of test functions. You compute rho tier phi, and then you also compute rho tier n of phi. Take the difference between the two of them, and you take the expected value of this quantity. So if I fix y, so from now on, just think of y as being fixed. This quantity is a number. This quantity is deterministic. What will happen, there's randomness in the approximation. So what I'm doing, what you can do, you can take the expected value of these quantities over the randomness in the approximating measure. That's one way. And then you can take the supremum of all these quantities over phi, as I said, for example, continuous and bounded with supremum norm equal to 1. Please note that I cannot take the supremum norm inside in here. I'd love to, but I can't take the supremum norm inside here, because effectively this will mean that I'm computing inside here the total variation norm, which I know that is infinite. So the supremum norm has to stay outside. And the other thing is, you could take the expected value not just over the randomness of rho n, but over all the possible realizations of the observation process. And then you can, so in this way you can obtain results that some of them are quenched, if I can use some of these notions. So this is where y is fixed, and some of them are annealed, which means that the averaging is over all the realizations of this, the driving Brownian motion W. If you really want a distance, to get a distance, a specific distance out of this, what you can do, you can take a countable sequence of test function phi that form a separable set. That means that if rho n t of phi k converges to rho t of phi k for any k, that means that in the weak topology I have convergence, and then you can manufacture this distance in this way, and this is a suitable distance. You can obtain results related to this distance from the previous from results coming from estimating the error in this way. And whilst this is nice and it looks okay, your results basically depends upon the choice of phi k, and therefore this distance is not really an intrinsic one. You affect the way in which this is measured, and it's not ideal. There are some other problems that this distance have, and in some sense it is, in my opinion, an open problem how you actually compute the error, how do you approximate the error. And the problems are as follows. In what you'll see, what I'm going to talk about, I will always say, this approximation is better than this one, this performs faster than this one, and so on. And all of the things that I'm going to say, you'll see that the heuristics are right, the numerics are right. However, because of the choice of the distance, there are no theoretical results that will justify what I'm going to say. So even though for each of the results that I'm going to show you, I'm going to be able to obtain bounds for these two quantities, right? So it's going to be clear that this distance or this measure will go to 0. This choice does not allow us to compare different approximations. This choice does not allow us to compare different approximations. And even more, what you like to do is that once you have rho t, you like to say, well, which one, what point in Bn is the closest possible one? you'd like to obtain the optimal approximation in Bn, and that cannot be done. It's still an open problem if the choice of the distance is this one. Also, we have a problem with the asymptotics of this. So most of the results are of the form, this distance is of order 1 over square root of n, and you'll have a constant in front of it which depends on time, and the constant, it cannot be explicitly computed. It's very difficult to access the actual constant. All you get is upper bounds. Now, as a result, what happens, you don't know what is the asymptotic behavior of this. Is it the case that these two manifolds diverge from each other, or is it the case that just they stay close to each other, or are there situations where the manifolds get closer and closer without increasing n? So all of these things are open problems, and the source of all these open problems is this choice of the distance, which is, as I said, not ideal. But let me just show you what the results are, and let me start with the first of the two approximations. So as I said, we are working with, so this is the first approximation. It's a Monte Carlo-based approximation, and the base of this is the Feynman-Katz formula that you just seen. So once again, to recap what I want to do, I want to take copies of the process x, and then for each of the copy of the process x, I want to compute this exponential as a weight, and in addition, I will add a second procedure that will keep the variance of the whole system in check. So as I said, my approximations belong to Bn. In other words, both rho n and its normalized version are of this form. So empirical distributions of some particles that evolve in time and carry different weights. For the normalized version, the sum of the weights is going to be 1. For the unnormalized version, the sum of the weights are not going to be 1, but they are going to be proportional with a single quantity. So what we do, we introduce a partition of the time interval. Okay, so at time 0, we start by what you do. You take rho 0, you take the solution of the Zakai equation at time 0, you normalize it, and then you sample independently from it n times, and you obtain the initial positions of the cloud of particles. And obviously, the normalized version of the solution, you just take it to be the sum of 1 over n times the corresponding Dirac measures. And to start off the approximation for rho, you start with this common constant. So we are assuming that we know what rho 0 is. So you know what the total mass is, divided by 1 over n, and multiplying by the corresponding Dirac measures. Okay, so this is what happens at time 0. And then let me explain what happens in a typical intervals. I initialize the system, and then I'm going to explain what you do in a typical interval, I delta, I plus 1 delta. So during the interval, what you'll do, as I just said, we just follow the law of the signal. So this is exactly the law of the signal. So each particle satisfies an SDE. It's a Markov process whose infinitesimal generator is the process A. We make the point here that each particle is driven by a Brownian motion on Wj, and all of them are mutually independent, and they are going to be chosen independent of the driving Brownian motion, the one that drives the SPDE. So that when I start averaging these particles, in some sense the randomness disappears, and all what I'm left with the deterministic part of the SPDE. And everything that happens in here, these Brownian motions are chosen independently of W and any other random variable that appears in the systems, and you'll see what other random variables appear in the system in a minute. Now, as I said, the second step is to put this exponential in place. So we need to compute this exponential. So what you do, you compute the exponentials, but only the part of the total exponential that corresponds to the small interval I plus 1 over delta. So whilst in here I had an exponential that starts from time 0 up to time t, what I do in here, I don't start with the exponential from time 0, I start with the exponential from time I delta, the beginning of the interval, and then just run it, compute the exponential over the small interval I plus 1 delta. Okay, now I can normalize, and I'll do that. So I take the exponential and normalize by the total sum. I take the exponential and normalize by the total sum. And then what I'll do at the end of the interval, I want to do something so that the particles that have the biggest exponential will influence more will have a much bigger influence than the particles that have a smaller exponential, right? And the reason is that if you don't apply this procedure, and you just, compute different trajectories, independent trajectory of xt, and compute the corresponding exponential, this quantity here is an exponential martingale. The variance of this thing goes to infinity, blows up, and it makes the whole sort of Monte Carlo method being useless. And the reason is that, well, as a way, so the law of x, the law of the signal, and the law of the SPDE, and the solution of the SPDE, they become very quickly singular to one another. And if you just insist on sampling from the law of the signal, you'll end up in the wrong place very quickly. So what you do, you say, well, okay, I don't want to end up in the wrong place, and I somehow want to try to keep tracking, evolve according to the law of the SPD. And the way to do that is to make sure that we always keep the particles with the bigger exponential. So how do you do that? At the end of the interval, you will look at these quantities, and you apply a randomized procedure to pick up the particles that have bigger weights. You pick up particles that have bigger weights. In other words, to pick up the particles that are well into the support of the solution of the SPD. So how do you do that? You do it in a way in which, so this is a random procedure. There's randomness introduced in the system at this stage. You do it in such a way that for each, if you look at one particle, you replace each particle and its corresponding weight by a number of particles of mass 1 over n, each one of them, so that the expected value of the number of particles divided by n is exactly this. So on average, you don't want to make any mistakes. You introduce a randomness, but the randomness is unbiased. But you replace this weight by several particles depending on how big the weight is. Now, the way to do that is, what we use here, we call it a branching mechanism. And the reason why you call it like that is because initially we were inspired by the work of Dawson and Watanabe of constructing a super process. That's where we come from. And so you want to do that. You want to do this. You want to do this branching so that you introduce the minimal amount of randomness in here. So I want to be as close as possible to my weight here, multiplied by the number of particles. So what I'll do is each offspring, the number of offsprings for the jth particle will be the corresponding weight multiplied by n, but integer part of that with this probability, or the integer part of that plus 1 with this probability. And if you compute the expected value of this random variable, you'll find out that the expected value of this random variable is exactly the weight multiplied by n. Okay? And this is the one that minimizes the variance, that minimizes the randomness introduced in this stage, and sort of numerical experiments confirm that this is the optimal way to perform this procedure. Okay, so you do that, and once you do that, so let me just say a few things about the choice of the number of offsprings. You want the sum of the total offsprings to be equal to n. You want to keep the number of particles constant. And what you want to do, and the reason why you have to introduce this branching procedure is because, as I said, you want to keep the particles in the support of the solution of the SPDE, not in the support of the solution of the diffusion process. Okay, and to do that, basically, you just eliminate particles that have small weight and multiply the particles that have large weight, and you have to make sure that the randomness that you introduce in the system at this level is minimized. And the way to do that is there are two algorithms that minimize the randomness. One was introduced by Terry Lyons and myself, and we called it the tree-based branching algorithm. I guess you can surmise from this that there's a tree in there. And the second one is a genetic algorithm that was introduced by Whitley in 1993. And there is no time to explain how one does that, but we've written out a pseudocode for the algorithm, which is very easy to implement, and it requires at most n-1 step if you start with n particles. Okay, so I've told you what the algorithm is. Then what is the approximation? So to approximate, first of all, to approximate the normalized version of the solution of the SPDE, what you do, as I said, you take the position of the particles constructed in this manner, look at the Dirac measure at these positions, and multiply each position with the normalized weights. Now remember, just after branching, the normalized weights are going to be equal to 1 over n. And this is how you approximate the normalized version of the solution of the SPDE. In order to approximate the SPDE itself, you multiply what you had before by one constant. So this is going to be common to all the particles, and this constant is an approximation of the total mass of the solution of the SPDE, and it's given in this format. It's simply a product. It's simply a product of averages of weights. And the theorem here is that under certain constraints, if you look at the mean square error, of the approximation of the solution of the Zachariah equation for a given specified test function has this form, is of order 1 over n, multiplied by the supremum norm of phi if phi is bounded. If phi is not bounded, you have to change this norm to some sort of LP norm. And if you can deduce from here, you deduce the L1 norm, the error when approximated the conditional distribution of the signal using this approximation is of order 1 over square root of n. Okay, so this concludes the first method. Now let me say a little bit about the second method. Now, the second method is again based on the Feynman-Katz representation, and I'm writing the Feynman-Katz representation in there. And again, I'm making the same point. The point being that if you look at this representation, this is simply let's pretend that W is fixed and given to us. It's simply some sort of functional of expected value of some sort of functional of the process X. Of course, it depends on the driving noise W. But on an abstract level, how do I approximate rho TFI? Well, I need to do two things. One is to get a simpler version of this. So, one that, for example, will depend only on the value of X at specified points. One that will depend only on the value of the driving noise at specified points. And then once you do that, you will have to find a way to approximate the law of x. Now, in the previous approximation, we used Monte Carlo method. We just sampled from the law of x. Here, we do not sample from the law of x. We use the cubature method introduced by Lyons and Victoire. Okay, so I need to tell you two steps. I have to have two steps. One is the step that discretizes this thing, which replaces the initial functional by one, which depends only on certain values of x corresponding to a partition. And the second one, I need to tell you how I'm then approximating the law of x at those values. In other words, I need to tell you, hopefully, a little bit about the Lyons-Victoire cubature method. Okay, so how do I discretize? How do I discretize the functional? And I know we've chosen a very simple way to discretize this. It's very obvious. So all you need to do is you take the stochastic integral and you replace it by the e to approximation. So you just take the sum of the gamma k at some times of the partition times the corresponding increment w to the partition, and then you can discretize this other integral as well. You just take the Riemann approximation. So the first question is, if you do that, you get an approximation to this guy depending on the mesh of the partition. How big is this error? How big is this error? Well, it turns out, so this is what I'm explaining in this. You get an equidistant partition, and then you look at these increments of the driving Brownian motion. You define this function gi in this format, and exactly what I told you before, you can write the discrete version of the functional by using this operator. So eventually you end up showing that the expected value of phi of xt times this discretized version of the z that I explained on the previous page. You can write it as the expected value of a number of random operators. These are going to be random operators, non-Markovian operators applied to the test function phi, estimated at x naught. And the condition is just to remind ourselves that I have randomness in the system, which now is fixed. The randomness in the system is fixed, right? And everything else depends on this given trajectory w. Okay? So I now I have this approximation of the solution of the Zakai equation, which if I normalize, I can get an approximation of approximation of the conditional distribution of the signal.
Question: what are gamma j's?
The Sensor functions. Gamma j's are the components of gamma in here, or the thing that appears, the zero order terms in here. Okay? So what is the error now? Now please remember that at this point in time, this is still not implementable, right? I cannot yet use my computer to construct this thing, because I have to find a way to compute this expected value, right? All these expected values. So this is I still have to do another step to use the cubature method to get to approximate the law of the signal. Okay, but at this point in time, let me just ask, what is the error here? Now, when we started looking at this, we found the result of Picard, which introduced the error under some conditions which were very, very difficult to check. So, kind of I've been forced to look into this and try to deduce the error, to try to find out what the error is. And the results of this were quite surprising. Now, you can think of if you assume very little about the coefficients, right, then the error if you look at the mean square error, the mean square error is of order 1 over n. The mean square error is of order 1 over n. Okay? So this is, in some sense, the most general result that you end up with under very, very general conditions. But if you assume a little bit more, if you say something about these moving properties of the semigroup associated to the signal process, for example, if you assume that the Hormander condition is applied, to the vector fields that generate the diffusion process, then the mean square error is has order nearly 1 over n squared. Not quite 1 over n squared, nearly 1 over n squared. And if you look at the paper, you will see that in some ways, this is sharp. You cannot get better than this. And by the same measure, the L1 norm, when you do this, is of order nearly 1. And in the best possible scenario, and that's where I'm assuming that the sensor function is twice differentiable. And now, if you were a practitioner, you will stand up and shout at me, how can I assume that? In general, this may not be the case. But if you assume that the gamma i's are twice differentiable bounded with bounded derivatives, then the mean square error is of order 1 over n squared, and the L1 norm is of order 1 over n. So you have different rates of convergence in there. Okay, so that's the error that you incur when you approximate the original functional. Now let's see what happens. Okay, so this is just the statement of Picard's result, and he proved everything under this condition, right? So I tried to understand this condition, and I simply failed. I think it's a very difficult condition to check in practice, unless gamma is bounded. Okay, so as I said, this is just the first step, the step where you just approximate the functional. In the second step, I have to approximate the law of the process X. I have to approximate the law of the process X. And to do that, as I said, I'm using the cubature method developed by Lyons and Victoire. There are some other methods that can be used interchangeably at this stage. So the idea here is that you go back, and this is exactly the stochastic flow associated to the diffusion process X. I'm writing it here in Stratonovich format. And then what I'm going to do next, instead of taking expected value of my functional of X with respect to the Wiener measure, I replace the Wiener measure by another measure called the cubature measure. Effectively, what they do in here is the following: they replace the driving Brownian path with a path which is a lot simpler. For example, for the cubature of order 3 and dimension 1, they take straight paths. They simply take straight paths. They replace the Brownian path with straight paths, right, which have equal weight. So each of these equations will split up into 2 equations, each one of them which is driven by a path that goes either up or down. Okay, and you sort of take the sum, the linear combinations of these 2 paths. In higher dimension, you have to use several paths, and the estimation that we have is that you have to use this many paths. So the number of paths here increases with the dimension. Please remember, this is not a Monte Carlo method. I do not have n particles in there. The number of paths is dictated by the choice of the cubature method. Okay, so there's a whole class of cubature method. They run in odd numbers, 3, 5, 7, and so on. And the reason why they run in odd numbers is because if you look in the proof, you need to use a stochastic Taylor expansion, where you cut off at level 3, level 5, and so on. And since I have run out of time, I just quickly, the idea is that I take the previous operator which I described, and I didn't have time to explain them very much, and all I do is replace the expected value with respect to the winner measure by the expected value with respect to this cubature measure. I compute similarly the corresponding approximations, wherein here I get these operators instead of the original ones, and the result is as follows. If you take the approximation that you get by discretizing the functional and compare it with the approximation that you get by discretizing the functional and implementing the cubature method measure, then you obtain something like this. See, this is a high order method, depends on the choice of the cubature method, right? So you get here, if m is equal to 3, you get something of order 1 over n, or you can go to 5, 7, and so on, and you can get as good as you want, right? So that's the error when you have replaced the law of x by, well, the winner measure by the cubature measure. When you go and compute the result and put the two together, you obtain something. Even in the best possible scenario, you obtain something which is of order 1 over n, and that's because, you know, we have to tag along, we have to carry with us the big error that's coming from discretizing the functional. And a similar result applies when you compute the corresponding unnormalized version of this. In other words, the similar result applies when you go and solve directly the Sakai equation. Well, I don't know if I convinced you, but the cubature method is essentially a deterministic method. It uses a set of ODEs to solve the problem. When you apply it to the filtering problem again, you end up with a deterministic algorithm, provided you kind of know or approximate the law of x naught with a deterministic approximation. There is a computational effort that you have to control in there, because you end up with a tree for which the number of branches increases exponentially, and then at that point you have to do something about this, and there are various methods to do that, which I enumerate here. So I should stop here. Thank you very much.
Thank you very much. Thank you. And so we have time for questions and comments. I was always asking myself, what is the relationship between your method and what Istvan was talking about? Is there any comparison known?
Well, that's a great question, and the answer is that I mean, it's on the cards. I'd love to find a way to compare, PDE-based method, grid-based methods with this type of methods. The common factor is that, in this type of methods, the grid can be thought of as a cloud of particles. So you can rewrite everything in terms of particles, and this could be the basis of comparing these methods. But as of now, there are no suitable ways to compare methods that come from different areas. I've just made a point that there are no suitable ways to compare different methods within this area.
Thank you. More questions? No? So I think we need to thank the speaker again.